Alright, so in this video we're going to start our next unit. This is unit 3 of the semester, and the name of this unit is called Thermodynamics. Okay, and so thermo means heat, and dynamics means basically the study of motion or why things move. And so thermodynamics is the study of heat and how and why it moves between objects. Okay, and so in this unit, we're going to be talking about things like heat and temperature and the laws of thermodynamics and different forms of heat transfer and how heat affects the temperature of an object. Okay, so those are all things that we'll be talking about in this unit. Relatively speaking, this is a pretty simple, straightforward unit. There's not a ton of calculations in this unit, but there are more conceptual things, and there's just kind of like vocabulary terms that you need to know and definitions you need to know and concepts you need to understand. And so this unit is going to be, there's still going to be some equations, but there's only going to be like a couple equations. And it's going to be more like conceptual and understanding type things. All right, so just kind of keep that in mind. Now, just a recap, or this should be a recap because you should have learned this like in your past science classes. All right, so all objects are made of atoms, okay, or combinations of atoms in motion. And there's different types of atoms. In fact, there's a whole periodic table full of different types of atoms, everything from hydrogen, helium, to nickel, iron, copper, magnesium. All those different elements are different types of atoms. Okay, so all objects in the universe are made either of atoms or combinations of atoms. Now, combination of atoms, we call those molecules. And so, for example, you know water is H2O. And so water is a molecule that's made of three atoms. Okay, so two hydrogen atoms and one oxygen atom make up one water molecule. Okay, and so all objects are either made of atoms or these combinations of atoms that are called molecules. You should also know, you probably learned this in like elementary school, that objects can exist in different states of matter depending on their formation. Okay, so you have solids, liquids, and gases. Those are the three basic states of matter. Now, there's other states of matter that we're not going to talk about, but those are the ones that you need to know about. All right, so those are all things that you should have learned in past science classes. And so with that in mind, we're going to use this prior knowledge to build our understanding of heat and thermal energy and temperature. Okay, so please make sure you take really good notes as we go through these slides because again, a lot of this unit is things that you just need to know or understand rather than calculation based. All right, so we're going to start off by taking a look at a simulation. Okay, and I'm going to link the simulation so that you can play around with it on your own. You can change the temperature. Basically, there's like a container of atoms, and you can change the type of atoms. You can change, neon, argon, oxygen, um, water. Okay, so here you have water molecules, and so the individual balls are atoms, but notice that they're kind of grouped up together, so those are molecules. And you can either add heat or you can decrease heat. Okay, and so we're going to do argon just because it's easiest to see, but I want you to play around with this and see if you can answer these three questions right here. What do you notice about the motion of the atoms at 0K? So when it says 0K, that's a temperature, and we'll talk more about what that temperature means. But here it says 43K, but if we cool down the atoms, we can decrease the temperature. Okay, so what do you notice about the motion of the atoms at 0K? As you heat the atoms, that is, as you increase the temperature, what type of energy are you adding? And then as the temperature of the atoms increase, how does their motion change? So I want you to play around with the simulation and try to answer those questions on your own. Okay, so let's go through the simulation together and see if we can answer these. Okay, so the first question said, what happens at 0K? 0K stands for 0 Kelvin, and this is what's called absolute zero. And I want you to see why it's called absolute zero. Okay, so notice that if I cool it down enough so that the temperature becomes 0K, 0 Kelvin, okay, the reason this is called absolute zero is because if you look, before the atoms were kind of like vibrating a little bit, they were shaking, they were moving. Okay, at 0 Kelvin, this is called absolute zero because this is the temperature at which the atoms or molecules stop moving. And so this is the lowest possible temperature these atoms could ever have because that's where their motion stops. Now, as I increase the temperature, Notice that now I'm at 7 Kelvin. Okay, so slightly warmer. Notice that the atoms are kind of vibrating in place. Okay, this blob of atoms is kind of moving up and down. Ignore that. Look at the individual motion of the atoms. Okay, they're shaking. Now the second question said, as you heat the atoms, what type of energy are you adding? So think about what type of energy we've talked about that has to do with motion, right? Because when I added a little bit of heat, the atoms started moving faster. So what type of energy has to do with motion? Okay, well that would be kinetic energy. And so as you add heat to the atoms, you're increasing the kinetic energy of the individual atoms. You can see they start to shake faster, they start to vibrate faster. Okay, the last question says, as the temperature of the atoms increase, how does their motion change? Okay, so we can see they start to vibrate faster, but look, they're starting to vibrate so fast that they're kind of starting to come apart. Okay, and so before I had a nice organized collection of atoms in a solid, right? But if I increase the temperature too much, they start to move faster and faster. And if they move too fast, they start to kind of separate from each other. Okay, and so notice I've increased the temperature a little bit, right? But they're not like a nice organized blob like they were before. Okay, and so this is what we would call a liquid. Okay, in a liquid, the atoms or molecules are still held together by electrical forces, but they're not nicely organized, right? Because the temperatures increase to the point where they're shaking themselves out of their nice organized structures. And so this is like a liquid right here. Now, as I increase the temperature more, as I add more and more heat, they're going to shake faster and faster, and at some point they're going to shake so fast that they literally break apart from each other. Okay, and so that's what you see happening there. Okay, so now the atoms are trying to get so much energy, they're literally like leaving their neighbors because they're moving too fast to be connected. Okay, and this is what we call a gas. Okay, so in a gas, all the atoms or all the molecules have so much kinetic energy that they separate. Okay, and you can play around with the rest of the simulation on your own to see, what's the difference between argon, neon, oxygen, water, etc. Okay, but that's just to kind of dip our toe in the water of thermodynamics. Now let's talk about some vocabulary terms. Okay, so the first term is a really important one. This is what's called thermal energy. Okay, and the definition for thermal energy is on the page. Of course, I would recommend that you add that to your notes. But thermal energy is defined as the total energy arising from the kinetic energy of its individual atoms, molecules, and ions. Okay, now the simplest way to say that is thermal energy is the total energy of all the atoms making up an object. In other words, if you find the kinetic energy of each individual atom and you add all those kinetic energies up, that total would be the thermal energy. Okay, so if I have like a container that has, let's say, a trillion atoms, I find the kinetic energy of each individual atom and I add all those up, that number would be the thermal energy. Okay, so thermal energy is the total energy coming from the kinetic energy of the atoms, molecules, and ions. Okay, and so very simply, the faster they're moving, the more thermal energy there is. Okay, the more particles there are, the more thermal energy there is. Right? Because if you're talking about total, you're adding up all the kinetic energies. If you have more of them, obviously you're going to get a bigger number. Now, another word people associate with this unit is heat. And so what is heat? So heat is the transfer of thermal energy from one object to another. So when we heat something, we're adding or subtracting thermal energy from an object. In the last unit, we talked about work. Okay, so work is the transfer of mechanical energy to or from an object. Heat is the transfer of thermal energy from one object to another. All right, so we have thermal energy, we have heat. What about temperature? Okay, so temperature also has a specific meaning. Okay, here it is. Again, I would always recommend that you put vocabulary terms in your notes. Okay, so here's the definition of temperature. Temperature is a number that measures the average kinetic energy of the atoms or molecules of an object. Okay, look at the keyword there. First of all, it doesn't say temperature is the average kinetic energy. It says is a number that measures the average kinetic energy. Second of all, that word average is different than the word total that we saw for thermal energy. Okay, so temperature has to do with the average kinetic energy of each of the atoms or molecules, whereas thermal energy has to do with the total amount. And so are temperature and thermal energy the same thing? No. Okay, they have two completely different definitions. Remember, the thermal energy is the total kinetic energy of all of an object's atoms and molecules, and temperature measures the average kinetic energy. So for example, you could have, let's say, 2 cups of water, and let's say each cup of water you put a thermometer in, they have the same temperature. Okay, just because they have the same temperature doesn't mean they have the same thermal energy, right? How can that be that you have 2 cups of water with the same temperature but different amounts of thermal energy? Well, clearly, the bigger cup on the left has more atoms, right? If they have the same temperature, that means on average, the atoms have the same energy. But if you have more of them, then you would have a higher thermal energy. Okay, and so you can have objects that are the same temperature, but that doesn't mean they have the same amount of thermal energy in them because you could have different numbers of atoms as well. All right, so quick recap, we talked about thermal energy, we talked about heat, and we talked about uh, temperature. Okay, now really quickly, we're going to talk about different temperature scales. Okay, the one we use in this country is called the Fahrenheit temperature scale. Okay, the Fahrenheit temperature scale is kind of strangely defined. Okay, but basically in the Fahrenheit scale, the freezing point of water is 32 degrees and the boiling point of water is 212 degrees. Okay, that's why when it's cold outside, if it gets below 32, that's when you have a possibility for like snow or sleet or icy rain because that's below the freezing point of water. And water boils at 212 degrees. Now, I only mentioned Fahrenheit because that's what we're used to dealing with in this country. Okay, and so for example, when you're sick, you take your temperature, it's 98.6, but that's in the Fahrenheit temperature scale. Okay, so 98.6 degrees Fahrenheit, that's what your body temperature should be, assuming that you're not sick. Okay, room temperature is about 68 degrees, etc. Now, we don't usually use Fahrenheit in science. Okay, we usually use either Celsius or Kelvin. So in the Celsius temperature scale, they define that so that the freezing point of water is 0 degrees and the boiling point is 100 degrees. Now, to me, that makes more sense, right? 0 and 100 makes more sense than 32 and 212. But again, in this country, we don't use Celsius. Now, if you go to Europe, then typically in other countries, they use the Celsius temperature scale. And so if you go, let's say to like France or something, and they say like, oh, the temperature is like 37, it sounds cold to us, but if it's 37 Celsius, that's actually about 99 degrees Fahrenheit, which would actually be really hot. Okay, so sometimes you see Celsius in science, um, but the SI unit, the scientific unit for temperature, is called the Kelvin temperature scale because it's based off of what's called absolute temperature. We talked at the beginning of this video about absolute zero, which is the lowest possible temperature an object can have, because absolute zero is the temperature where all the motion of the atoms or molecules stops. Okay, that is the absolute lowest possible temperature, like in the universe, like by definition. Okay, that's what's called absolute zero. And by absolute zero, we mean 0 Kelvin. Okay, and so that's why the Kelvin scale is used in science because it has that 0 Kelvin as the lowest possible temperature. So you can't have a temperature lower than 0 Kelvin. Okay, not because we're not trying enough, but that's basically how it's like defined. It's defined in a way where like 0 Kelvin is the limit to temperature. All right, so make sure you have that information in your notes. Let's see, we talked about temperature and thermal energy already, so this is not new. Just because two objects have the same temperature doesn't mean they both contain the same amount of thermal energy. So for example, if we have a piece of lead and a piece of tree sap, okay, they have the same temperature, right? All that means is that those atoms have the same average kinetic energy. Okay, but it's possible that the tree sap has more thermal energy in it than the lead. Now, how is that possible? Well, most likely the tree sap has more atoms in it. right? Because we talked about how thermal energy is the total kinetic energy of all those atoms or molecules, whereas temperature only measures the average amount of that. Okay, so the key idea there is that thermal energy and temperature are not the same. All right, and just two more quick slides. Again, we're just kind of doing vocabulary in this introduction video. So, when two objects are able to transfer thermal energy between them, we say they are in thermal contact. And so, just to give you an example, if you like, let's say, you put an ice cube in a cup of coffee, or you touch the stove for some reason. If objects are able to transfer like thermal energy between them, heat, we say they're in thermal contact. Now, normally what happens when you have two objects in thermal contact is that heat is going to flow from one object to the other object. Now, the direction of that is really important. Heat naturally flows from hot to cold. Okay, heat will flow naturally from the hotter object to the colder object until they reach what's called thermal equilibrium. Let me give you an example. Let's say you take an ice cube and you put it in your hot soup. Okay, so if you have soup that's hot and you have an ice cube that's cold, heat, thermal energy is going to come out of the soup and go into the ice cube. Okay, that's going to happen naturally. Now, that's going to keep happening until they reach what's called thermal equilibrium. Now, thermal equilibrium has a special meaning. That is the state in which two objects have the same temperature and have no net heat flow between them. Okay, so eventually that ice cube is going to melt and it's going to reach the same temperature as the soup. Okay, just to give you another example, if you take your hot soup, if you just like leave it on the counter and you come back like 2 hours later, it's been in thermal contact with the air in the room. And so if you come back after 2 hours, most likely the soup is going to be the same temperature as the air in that room because they're going to be in thermal equilibrium. Okay, and so if you have two things in thermal contact, heat's going to go from hot to cold um, until they reach that point where they have the same temperature and there's no net heat flow between them. That's called thermal equilibrium. All right, now I say heat naturally flows from hot to cold. You can force heat to go from cold to hot, but you have to have like an engine or a pump or something. That's kind of like how like AC works or refrigerators work. Okay, so it's not that you can't make heat go from cold to hot, but it doesn't happen on its own. Okay, it doesn't naturally happen. All right, so one last term I want to talk about besides thermal equilibrium is pressure. Okay, and we're going to talk mainly about the pressure of a gas. All right, so I want you to see what pressure looks like. Now, here's the definition of pressure. It says when a substance exists as a gas inside a container, it has a certain pressure. It says the pressure of a gas is a number that measures how frequently, that means how often, the gas particles collide with the container walls. Okay, so I want you to see what this looks like. All right, so here's a gauge that measures pressure. Notice right now the pressure reads 0. I'm going to heat up these neon atoms. Now notice as long as the atoms are solid or liquid, there's no pressure. Okay, but watch what happens when these particles hit the container walls. Look, it went to 0.4. Now it's back to 0. Okay, so what I want you to see is every time one of these atoms hits the container walls, like make it do it. Right there's a little bit of pressure. Okay, now there's more hitting. Now there's more pressure. So there's a little bit of pressure every time one of those gas particles, because now it's becoming a gas, hits the container walls. The more often that happens, we say the more pressure there is. So as I increase the temperature, remember temperature measures kinetic energy. More temperature means faster atoms. All right, faster atoms means they're going to hit the walls more often. Okay, but there's other ways where I can also make them hit the walls more often. Watch this. Okay, so aside from increasing the temperature is obviously going to increase the pressure. But watch this. If I pump in more gas particles, watch what happens. Okay, more gas particles means more often collisions. That means more pressure. So now you see the pressures going up. If you've ever had to like pump up a tire or like a bike tire, a car tire, or pump up like a soccer ball or something, you've experienced that when you pump it up, the pressure gets bigger. That's because there's more gas particles bouncing off inside that soccer ball that you're trying to blow up. That's why the pressure's more. Okay, now what can also happen is, let's say you're pumping up your bike tires, notice that because they're hitting more often, right, the temperature is also increased. Okay, because if they're hitting more often, that means they've got more kinetic energy, so the temperature is gonna go up. That's why if you pump your bike for long enough, that you actually feel the bike pump gets a little warm. Okay, and the last way I could increase the pressure if I wanted to is if I decrease the volume. Okay, if I make the space smaller, right, obviously they're going to hit more often. Okay, so here the space is smaller, they're hitting more often, the pressure is getting way higher, and if the pressure becomes too much, then bad things can happen and things can explode, like you can see there. All right, so that is the basics of thermodynamics. Okay, make sure you add all the vocabulary terms to your notes and make sure you go back and review the PowerPoint or the video if you have any more questions. As always, please let me know if you have any questions, and I'll see you guys in the next video.